another lesson related to radical functions. Today we are going to be talking about graphing radical functions, and we will also be including some discussion on what it means to be an even versus an odd function. So the first thing I want to just show you is all the different ways we can describe or write in function notation the transformations of functions. Now, just keep in mind that basically we've got two categories. We have horizontal transformations, and so those are the things that happen inside the function, whether we're talking about our reflection or our dilation, and our vertical transformations or translations. Now, keep in mind a reflection could be both. It depends on where that negative is located. Same thing with a stretch or a dilation, depending on what word we want to use for that. But those things, remember, they happen outside. Okay, so we're looking at things that happen outside. That's our vertical. And then things that happen inside are our horizontal. All right. If you want to write down any of this information, be my guest, but we've definitely written this notation down before. The only other comment I will make about it is that when we're talking about being inside or outside, because we are talking about radicals, we are talking about whether or not we are outside or inside the root. Okay, so now the root becomes what we are either inside or out of. All right. So some new information is, and not so much new, but just to revisit it and make sure we've got a clear understanding of it. We've got our parent function for our square root function and our cube root function. Okay. Now keep in mind, if you forget what a particular function looks like, you can always just build a table of that function. So for example, we're taking 0, substituting that in, that's how we get 0 out for one of our key points on our square root function. 1's another good point to put in because the square root of 1 is 1. And then the next point that I would look at would not be 2 or 3. It would be what we get when we substitute in 4, because 4, the square root of that value, is 2. So we have this ordered pair right here at 4, 2. And then after that, the next value I would substitute in that'd be worth it would be 9. And then that would be at 9, 3. Now, some things to keep in mind about the square root function. It has a restricted domain. Now, this is not written in interval notation, so I'm going to take a moment and I'm going to write this in interval notation. So from 0 to infinity for our domain. And same thing for our range. 0 to infinity. Now keep in mind that's because we're starting at 0 and we're moving to the right in our graph. If that initial point changes, shifts up, down, left, right, that will affect the 0, 0 starting point of our domain and range. And if it reflects, it will entirely change our domain and range. So just keep in mind that's the domain and range of the parent function, and it will always be restricted in some way, shape, or form. Okay, now taking a look at the cube root, keep in mind that the cube root, you can have positive and negative numbers in there because nothing is going to be imaginary. So when we go to make our table, we can have some positive and negative values. Now, I'm not going to do this in perfect order. I'm going to start with -1, 0, and 1 because those are values we can easily take the cube root of. They are the identical values. But the next number you'd want to go out to, we can't even see in our graph. It would be -8 or +8 because remember the cube root of 8 is 2. So the cube root of -8 is -2. So that is our table for the cube root function. And keep in mind that the cube root function, even though it doesn't look like it, it is very slowly growing. It is very slowly getting bigger and like smaller sort of in that height. So it will eventually reach all the real numbers, okay? And keep in mind the other way you can write all real numbers, I'm just going to write it up here, is the all real number r, or you can write -infinity to infinity, okay? Those are some other ways to indicate the domain is all real numbers. Okay. So now we're actually going to do a little bit of graphing. So we've got a function that's a square root, so it's going to look something like this, right? But it shifted right 1 and up 4. So that starting point is going to go right 1 and up 1, 2, 3, 4. So it's going to start right here. Once you shift it, you can follow the pattern from this table that we made to help you graph it. So you can go over 1, up 1. You can go over 4 and up 2. And you can go over 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, and up 3, right? And that's going to give you this half of a parabola type shape that makes that square root function. So notice now that our starting point is here at 1, 4, that's going to affect our domain, which is now going to be from 1 to infinity, and our range, which is now going to be from 4 to infinity. Okay? Hopefully that makes sense. Okay, we've got the cube root of 4x with the negative out front. Okay, so in this case, I'm actually going to make a table because these are some more complicated changes. So we're going to take the normal values. So here, I'll write them from least to greatest. -8, -1, 0, 1, and 8. And then -2, -1, 0, 1, and 2. And here's what's happening. All of our all of our y values are going to be multiplied by -1. So y, here I'll write this a little bit more clearly. It's going to be like -y here. So all the negatives change to positive. The 0 doesn't change, but now our positives become negative. And then inside, something that if you want to make a little note to yourself is true about this stretch. Whatever's happening with A, or B, if you want to use two different letters. I normally use B. It's always going to be the reciprocal, okay? So like, see how this says 3x, so it's really a shrink by a factor of a third. The same thing's happening here. We're taking all of our x values and we're multiplying them by a fourth. So now I'm going to have -2, -1/4, 0, +1/4, and 2, okay? So it's going to make all those values smaller. So then I graph the combination of those ordered pairs. So like 0, 0 didn't really change, but now I'm going to go to -2 and +2. And go to +2 and -2. And now you could go to a fourth and -1. And if it's not perfect, that's okay, right? Because we don't have an exact value for that. But if you'll notice, now my graph is making that S shape upside down, okay? And so then from there, I'm just going to extend my graph outwards, okay? So hopefully you can tell that the normal cube root function that goes like this, down and then up into the first quadrant, has been reflected, right? And kind of squooshed together a little bit near that origin. But luckily, our domain and our range, they don't change. They are still -infinity to infinity. All real numbers in both cases. Okay, now if we take a look at these next two graphs, you can keep g of x as written, or you could rewrite it as 3 times the square root, because that's what that 1/2 exponent is, of -x. Okay, totally up to you. So how about you take a moment and try each of those graphs for me, okay? And then I'll come back and we'll show you what they look like. All right, welcome back. So this negative means that all the x values are going to be multiplied by a -1, right? We're reflecting. So 0, 0 is still going to be the same, but when I go right, normally I'd go over 1, up 1, but instead I'm going to go left. And then when I go left, I'm also going to take all the y values and multiply them by 3. So instead of going 1, 1, I'm going to go 1 and then 3 units over. And then the next value I'd have normally gone to is 4. So I'm going to go 1, 2, 3, -4. And then normally I would have gone up 2, but instead I'm going to go up 8. So 4, 5, 6, 7, 8. And then at that point, I'm probably going to be too big to fit in the graph. So I'm just going to go up and out in that direction. So the biggest difference that we're going to notice here is in the domain and the range. So now we're ending at 0. So really we're going to go from negative infinity to 0, right? Because this area right here is negative infinity. And then our range, even though it looks like the graph's going backwards, our graph is still on the y-axis, still starting at 0 and going upwards, right? So our range is still going to be from 0 to infinity. All right, and hopefully you tried this next one also. And again, just to kind of mix it up, here I will do a table just to show you what that looks like. So this means our y values are going to be multiplied by 1/4, and this means we're going to move left 5. In other words, we're going to subtract 5 from every x value. So if normally I had 0, 1, and I'm just going to go 4, those 3, I'm going to subtract 5 from each of those numbers. That'll be my left 5. So now I'm at -5, -4, and -1. And then normally I have 0, 1, and 2. I'm going to multiply each of those by 1/4. So now those are at 0, 1/4, super tiny height, and 1/2. So when I put it all together, I'm at -5, 1, 2, 3, 4, 5. This is -5, 0. And -4 1/4. And then -1 1/2. So this guy is like super short, right? And I'm sure there's a few nicer points we could have plotted, but really that just gets you the gist of that. So that's what and our domain is going to be from -5 to infinity, and our range is very, very slowly going from 0 to infinity. All right, last thing to talk about here before we get into the whole even odd business is just descriptions. So, and adding more descriptions to a specific function. So if I want to add a vertical shrink by a factor of 1/3, that's going to go out here in front. If I want to translate 3 units right, that means I'm going to take this and I'm going to subtract 3 from whatever's currently going on. So I'm sorry. Yeah, I'm going to subtract 3 because I'm going to be moving right. This is already moving left 5. So there's going to be a net, loss of still some left business. So all in all, our function is going to end up being f of x equals 1/3 of the square root of, and here I'll show you what this looks like. It's x plus 5 minus 3. So that's why I said there's still a net left, because when I add those two values, those like terms together, I still have a positive 2. So I'm still moving left. I'm just moving less left. All right, in this case, I'm trying to reflect in the x-axis. So that means the y values are being multiplied by a negative. And then 2 units down, so that's a -2. So I'm subtracting 2 and I'm multiplying the outside by -1. So that ends up giving me a function that's -5 square roots of x plus 1. All right? Hopefully that makes sense. Okay, now I want to take a moment and I want to add a page, but I'm going to go back to these graphs for a moment, okay? So I want you to notice that one of these graphs only covers part of our picture, and one of the graphs cuts through the entirety, right? It cuts through multiple quadrants. So kind of keep that in mind as we're talking about even versus odd functions. So even functions have y-axis symmetry. That means for every point x comma y, there is an equivalent point at x comma -y. I'm sorry, I flipped that around. My apologies, because I was thinking about the y-axis symmetry. There's an equivalent point at -x comma y. A classic function that has even symmetry is the parabola. All right, because for example, there's a point at 2, 4, and there's also a point at -2, 4. And just because I don't want your mind to be totally melded, I will put the negative on the left side and I'll put the positive on the right side. That's even symmetry. Odd functions have what we call rotational symmetry. And so that means for every point x, y, there is a point at negative x, negative y. Okay? And so when we look at that cube root function, the fact that there is a point here at 1, 1, and a point down here at -1, -1, that indicates that we have odd symmetry, or an odd function, because we have rotational symmetry. So the way you test for even or odd functions is simple. Step 1, take f of x, whatever the function is, and rewrite as f of negative x, right? Because if you notice, the commonality is that x switches to negative x, and see what happens by simplifying the expression. Simplify the expression. If f of negative x equals y, then we're even. If f of negative x equals negative y, then, in other words, the opposite, then we are odd. If it's a combination, if neither y nor opposite of y, then say neither. All right. And we can also do this visually, right? What I just showed you with a graph, you can also do that test visually. So that's one of the reasons why we just did our little graphing test. For example, this function right here is odd because we have a point at -2, 2, and we have a point at 2, -2. Those are opposite points, so that is an odd function, okay? Our square root functions, that's not going to be possible because we only have a partial piece of the graph. If we had maybe a quadratic, we might be able to find some even functions, but they will be a neither situation. All right, folks, thanks so much for listening. Hopefully you got a little more clarity on how to graph, and I'm sure we're going to do more practice. So if you got questions, never keep them to yourselves. Always ask them. All right. Have a good rest of your day. Bye.